Let's start.
Should we start? Okay. Fine. So I suppose due to the bad weather, we have expecting more people to come at some point. But let's just start the workshop. First, let's welcome the CMSA Director, Professor Yao, to speak for us.
Welcome to CMSA. This is a center we set up 6 years ago for interdisciplinary research that are related to mathematics. So we have been very interested in condensed matter actually from the first day when we start the conference, the center, where we have Xiaodao actually came, and also Zhang Shou and Shou Xinzhang also gave the first major speech. Well, too bad he died. But anyway, this has been somewhat going on program that we are interested in mathematics in condensed matter. And some of them are more practical mathematicians, but we are happy to see mathematics are useful for condensed matter also. So we are very glad to have this conference, which is the second workshop we have in this year. So thank you.
So we will moderate the basic, and also the first speaker, Professor Emil Prodan from Yeshiva University. And you should introduce.
The first speaker is Professor Emil Prodan from Yeshiva University. Will speak about the topological correspondence correspondence.
Thank you very much. Thank you for the invitation. Thanks to the audience for making it. So here is the title of my talk. K-theory used for full boundary correspondence, and I am very sure that most of you here know K-theory from a classification program. But what I will show you today is how to use K-theory to, in fact, understand spectral problems and how to establish full boundary correspondence. And I should say that this goes back to 1980s, in fact, the second half of the 70s, when Jean Bélizard started this program, and he has the absolutely outstanding work, K-theory and C-star algebra in condensed matter physics. And then this work was followed by his student Hermann Schulz-Baldes and Johannes Kellendorf, who showed all of us how to use K-theory to establish full boundary correspondence. So what's the challenge? The challenge is we want to go away from periodicity and we want to establish the full boundary correspondence independent of the boundary condition we put. So we allow boundary conditions which are not clear-cut, they can have defects and so on. So I'll start first with a closer look at patterns. And here is the simplest case, the one-dimensional case. And the pattern is just this sequence of sticks. And as you can see, is not periodic, but because these points can sit on the real axis, we can order them, so we can put a label on this one, and the label is from the group Z. So later I will form a lattice, but keep in mind that this Z is only there to supply labels and not to enforce any periodicity whatsoever. So now, if I fix x0 always to the origin, which will be the case, then this pattern, in fact, is fully determined by the distance between the points. And all of a sudden, you see that, in fact, the distance can be seen as a point in an infinite dimensional space. And that's precisely how one should look at the pattern, as a point in a topological space. And then, if the pattern is rigidly shifted, so each point gets to sit at the origin once, then this point in R infinity traces a shape, and that shape is called the whole of the pattern. It will play a fundamental role. And the success of any program in pattern analysis is the computation of this whole, which can be as complicated as you want. And here is a definition mathematical definition of what a system or a pattern means to be homogeneous. It means that this dynamical system made out of pole and the dynamical action of the group Z is in fact topologically ergodic. So in physics we hear this terminology, but it's very vague, yet remember that there is a very precise mathematical definition for what a pattern means to be homogeneous. So I want to show you from the very beginning that this whole, here it's sort of very abstract. It's in fact very tangible. And here is a calculation of a whole using a computer. So here is a pattern, and like I said over here, this pattern is just a point in R infinity, and I have this shape inside this R infinity. How I'm going to see what this shape is? I will project this shape on first dimension, 2 dimension, 3 dimensions, so I can visually look at it. And here was what you get when you look at this pattern. When you project on 1 dimension, it's a line. 2 dimension, it's a circle. Now this circle might be a projection of a cylinder, but when you go to 3 dimension, you see that it remains a circle. And in fact, no matter what 3 dimensions you choose, it's always a circle, which tells you that the whole of this pattern is indeed a circle. Here is another pattern which use 2 theta's, all incommensurate, including the fraction. And in this case, the same procedure gives us a torus. And in fact, you can generate wholes with S complicated one. So the whole is tangible, and let me say that this whole, in fact, appends to the Brillouin torus, and you get extra dimensions. And in fact, the topological invariants which you can define for aperiodic pattern are much more interesting than the one for periodic patterns. So if I have pattern resonators, so I put them right on top of the pattern, and here are some facts and assumptions. The resonators are identical and have n internal degrees of freedom, these red lines. And then the dynamics, so these being atoms or photonic cavities or mechanical resonators, the dynamics takes into place in this Hilbert space. So obviously here I'm talking about linear regime if we are talking about classical mechanical system or about one particle picture. But the Hilbert space is just L2 over Z times the space which simulates the internal degrees of freedom. So vector looks like that from this Hilbert space. And a generic Hamiltonian on this space takes this form. So it's very, very generic. But one point to remember, P, in fact, is a variable. It lives on this topological space. And once the resonators are set, this Hamiltonian, that means these hopping matrices, are entirely determined by the pattern itself. For sure, if these are atoms, the electrons interact with Coulomb forces. You put them, arrange them in a pattern. The dynamics is truly defined by the pattern. Yes.
You require the short-range interaction, so only neighboring site can interact.
So I
This
will.
one
So
seems
here
very
is,
generic.
so here I'm not putting any short range, but I will require that there is a certain decay, but I cannot specify that decay quantitatively. The only thing I'm asking is that this stage is self-adjoint only. So now, can we say something about the spectrum of this guy? Can we say something what happens when we cut an edge? And all this in this generality. And at first sight, you'll say, no, it's impossible because this is so general. How can you say anything pertinent? But in fact, you can, because the algebra of observables where all these Hamiltonians live is very small. And here, how it comes about. Galilean invariance implies that if you shift these indices by an A, and you appropriately shift the pattern, then the Hoping matrices remain the same. So this is just shifting the pattern. And I'm putting here the term Galilean to remind that this will not be the case if my pattern sits in a background field. So Galilean invariance is important. And then if I take this A to be n, then one index can be dropped. And all of a sudden the Hamiltonian gets a structure. And it's a very particular structure. As you can see, we have over here a diagonal operator, and these guys all commute with each other, and here we have the shift operator. So all Galilean invariant Hamiltonians defined over a pattern, no matter what resonators I put, how they couple with each other, they are all drawn from this algebra, where A, as I said, is generated by the shift and commuting diagonal operators like so. So the algebra is very particular. Now there is a fact, any commutative C-star algebra is isomorphic to algebra of continuous functions over some topological space. And in our case, the algebra of these commuting diagonal operators turns out to be isomorphic with the algebra of continuous functions over the whole. And I just told you the whole will have a major role, and here it enters. So at the end, I can state very abstractly that the algebra which supplies any Hamiltonian over this pattern is in fact generated by a unitary operator, the algebra of functions over the whole, together with commutation relations. I'm not sure if we can get that one away. So then there is a commutation relation over there. What is it? If I take a function from here, a u here, and I put function first and u second, it's the same as putting u first and function, but function gets composed with the tau. So that was the mapping which comes from the whole. So that's the algebra. Let's compute one of these algebra, and you see a quite interesting connection. So I'm going again with this pattern. We just learned that the whole of this pattern is just a circle. So we saw this circle, and then the action of the z is just the shift by a theta. Now, the functions over the circle are generated by just one function, and we know that from Fourier decomposition, and this function is just this, it's the exponential of e to the pi x. Furthermore, I can verify what these commutation relations mean, and very simple algebra shows that the commutation relation between u and this function p, in fact, gives me the non-commutative two torus. So here is the, we learn that these Hamiltonians are drawn from the same algebra which gives us the magnetic translation. So the dynamics of electrons in on a two-dimensional lattice in the presence of a magnetic field. So if you are not convinced, let's diagonalize. I'm taking a generic Hamiltonian. In fact, it's not so generic. So the Hoping matrix is just a function of the distance between the points. And I can take polynomial decaying. Here I took a very fast decaying function. if I diagonalize this Hamiltonian and show you the spectrum as a function of theta, the Hofstadter butterfly shows. And in fact, you can change this one not with just a two-body potential, but you can change it with a three-body, four-body, and the type of the Hofstadter spectrum shows up. So I guess at this point everybody is convinced that there will be Chern numbers and other topological invariant Chern numbers associated with these gaps, and topological edge spectrum will show up for these patterns. And all of this just because we were able to calculate the algebra. Okay, how about this pattern?
Excuse me, on the previous one,
Yes.
the pattern is
There is a psi here.
let's see. So theta is some kind of irrational number here.
So theta is the irrational number, and psi is a phase.
Okay. If theta is a rational number, the thing will collapse.
So for sure, as I'm going over this part, I'm
Oh, yeah,
crossing
yeah,
rational
I
numbers.
see, okay.
I'm crossing rational numbers, so every time when you cross a rational number, then you see a finite number of solid bands. So how about this pattern? This is just a incommensurate bilayer. You take the same Hamiltonian, but now these points P are these points on this pattern. I cannot label them anymore. When you diagonalize the Hamiltonian, this comes out. How can you understand the spectrum, and what are we looking at? And the answer is like so. It turns out that this pattern, the whole of this pattern is this pretzel, and you can generate this pattern by just stepping by a theta on this pretzel. As a result, the whole is just, again, the circle, but the length of the circle is 1 plus theta. And the algebra of observables comes to be, again, the non-commutative torus, but with the theta prime, which is theta plus 1 plus theta. Let me remind you what theta is. So if this one is 2 pi, then the one above is a theta smaller than 2 pi. So at the end, what we are looking here, it's again a Hofstadter, an image of the Hofstadter spectrum with this axis rescaled. So, okay, now is the quiz time. Can you tell how the spectrum will look like when I evaluate the Hamiltonian on this pattern? And furthermore, if there will be topological edge spectrum when I cut this pattern. There are some regularities on this pattern, but you have to admit it's quite nasty. And I give you a hint. The pattern was generated in the following way. So I have a closed loop, and I have a point, and every time I'm moving the loop by a unit, and I'm shifting this point by the same length. So this shift plays the role of theta, and every time I'm going, I'm shifting by it. So in this case, in fact, you can see easily that the whole of the pattern is this closed loop. And the dynamical process is just a step by a theta. So here is the spectrum. It makes perfect sense. The algebra is again the non-commutative 2 torus by the same theta. All these gaps can be associated with a Chern number. There will be topological edge spectrum for this pattern. Let's look again at it. So I guess you will not be able to, without these methods, you will not be able to figure out this. So that was the case of one dimension, but the whole thing blows up in higher dimensions, and always the mindset should be that the pattern is a variable which takes value in a topological space of patterns. This space of patterns, in fact, can be defined very precise and is not just loose terminology. The generic Hamiltonian takes this form, and here is my preferred example. there is the labeling hypothesis. So things work when there is this labeling hypothesis. So imagine that the researcher examines a single pattern under a microscope, the pattern shifts and rotates, but the researcher always recenters the pattern with one point in the middle of the field of view, rotates it, and the key is that each point of the pattern can be labeled by an element of a discrete group. So I put this picture here, which shows the solidification of the table salt, and that's an X-ray diffraction pattern which can dig up the space group of the crystal very close to the melting point. So somehow, if you take a snapshot of the atoms, they are all over the place, yet the space group shows up in the diffraction pattern. How can that be? It's because the space group supply a label for these atoms, but it doesn't say that the pattern actually has the space group symmetry. So the hypothesis is that the resonator of the center, every point can be labeled and relabeled by a discrete group G. The resonator at the center always be labeled by the unit. If there are two patterns, so this researcher see two patterns, they can be connected by an Euclidean transformation, but on top of that, the labels, these two labels must be consistent, so there might exist a single G from the group, so that one label goes into the other one. In these conditions, and that was certainly true for the space group, then there is a canonical isomorphism from L2 of the pattern to L2 of G, and the Hamiltonian takes this form, and now I can repeat the whole story that I showed before. The Hamiltonian have a structure, this comes from the Galilean invariance, the Hamiltonian then reduces to this form, and we see that the Hamiltonian belongs to the algebra generated by these shift operators together with this diagonal. The whole of the pattern shows up again, so we learn again that the Hamiltonians belongs to a small algebra which in many cases can be computed explicitly. So a general framework to generate G-label patterns was supplied in this work. And in fact, in this work, we show that if we want to generate a pattern with this code, then there is an algorithm for it. But there are patterns which cannot be labeled by discrete groups. So example, it's an amorphous or a liquid substance. The atoms, no matter how well you try, you cannot label them consistently. And in this case, the algebra of observables is much, much nastier. It's a groupoid sister algebra which unfortunately are very difficult to work with. In particular, the K-theory is hard to compute. So I will always, for the rest of the talk, stay with this type of patterns for which can be labeled with a discrete group. In fact, my discrete group will always be the discrete translations. So I will summarize. So when the points of P can be labeled by ZP, I also put a magnetic field, and the algebra of observables is infinity, so this takes care of the internal degrees of freedom, plus A theta. A theta is just a sister algebra generated by D unitary operator plus continuous functions over the whole, and here are the connotation relations. The generic element of such algebra takes this form, where the coefficients AQ are functions and UQ is made out of these generators. The algebra is immediately equipped with a trace, and it accepts a family of representations, and these canonical representations gives me back the Hamiltonians. So in fact, I can forget about this representation and just work with the algebra itself.
Does the dynamic have an entropy?
Yes,
Would that refer in the algebra?
that will be.
Would that appear in the algebra or something like that?
So that will be only relevant at the classical degrees of freedom. Okay, so now we have this algebra, so what? The next tool one uses is the K-theory, and here I will only use the complex K-theory because I'm not using any symmetries would require the real K-theory. So just to recall, the K-naught group classify projections. So if you take an element from this algebra, when you square it, you get the projection again, and when you conjugate, you get the projection again. You call that a projection, and among the projections, you can set different equivalence relations. So here is the homotopy equivalence relation, here is the similarity equivalent relation, and here is the von Neumann relation. In general, these three are different, but if you tensor your algebra with the algebra of matrices of arbitrary large dimension, then all these three equivalent relations become the same. So if this defines a class relative to these relations, then the K-naught group is defined by the set of these classes together with formal addition, and the addition is just like so. So the concept is very simple. When you open a book on K-theory for C-star algebras, the concepts take 1 or 2 pages. The rest of the book is all about computing these K-groups. But here we will just take examples where the K-groups have been already computed. So what's the big picture? Separable C-star algebra have countable K-naught groups. So in other words, if we classify by K-theory, then we have, because of this countability, we can list, we can enumerate the classes, and this will be not the case if we will be working with von Neumann algebras. In that case, these groups will be uncountable, and the classification by K-theory makes no sense. So always we need to somehow cook up a C-star algebra. Here is an observation which says that, okay, the projection, which is just the indicator function of an interval on the Hamiltonian, belongs to the C-star algebra only if the ends of the interval is in a gap. So it means as long as you stay at the C-star algebra level, you cannot approach the case of dynamical gap, which is the case of strong disorder, where there is no spectral gap whatsoever, there are only dynamical gaps. Now, the thing becomes very useful when the K group has a finite number of generators. So if you take any projection from the algebra, then it can be decomposed, its class can be decomposed in terms of these generators. So all of a sudden these integer coefficients show up, and these coefficients represent all independent numerical invariants that can be associated to a projection. So I was mentioning the Chern number, but the big question is there anything besides this Chern number? And here is the answer. Besides these coefficients Cj, there is nothing you can associate with a projection. Now, along this, you will find the weak topological invariants and the strong ones. So and at this level, you cannot distinguish between them. And if the algebra happens to be equipped with a normalized trace, by just taking the trace on this projection, which is independent on which representative you take from the class, you immediately find an image of this K group as a countable subgroup of the real axis. And this is how we were going to look at these K groups. So, knowing the K theory, it gives you a global picture. You are already above, and you see what can be in this C-star algebra. In other words, we already know that the algebra is fully determined by the pattern. So once you identify these generators, you know that there is nothing else there, and you move on. You will not search for any other. So out of these generators, you hook up the model Hamiltonians, which can, and everything else is just layering of these model Hamiltonians. So K-theory gives you the global picture. The Lizard's gap labeling. So suppose I'm taking a Hamiltonian from this algebra, and G is a gap, then I can define the gap projection, just the indicator function for this interval applied on the Hamiltonian. And this projection defines a class in the K group. It has a decomposition like so. So a set of labels can be placed on this gap G. So every spectral gap can be uniquely labeled by such labels. Conclusion, the gaps are uniquely labeled by an element of the K0 group. Hence, when we look at the spectrum, as we did before, we really are looking at an image of the K0 group. To get the full K, always as we look at an image, okay, I only see the front of it. To see the back of it, I need to rotate it. So if I need to see the whole K group, I just need to take a few random Hamiltonians and just diagonalize them and see what kind of gaps appear. So this amazing principle was discovered by Jean in 80s, and he was trying to tell us, use it in condensed matter. Let's see for the our algebras turn out to be non-commutative tori. So let's go a little bit over this example. So it's an algebra generated by unitary operator like this, commutation relations, and the K0 group is z to the power 2d minus 1. It turns out that the generators can be labeled by a set of indices. These indices are from among 1 all the way to the dimension d, and you need this, the cardinality of this set to be even. If you count how many subsets are, you'll get that they are precisely 2 to the power d minus 1. So that's in fact all that we need about the K-theory of this algebra. And then if we have a trace, we know what is the value of this trace on the generators. It's just a Pfaffian of this matrix when these indices are inside this J. So this is what this theta J means. So let's see it at work. So here is this pattern. This pattern, in fact, can be dynamically generated by walking on a circle and projecting on the real axis. We learned that the whole is the circle, is this very circle. The action of the tau is the stepping by theta on the circle. And we learned that the algebra is a non-commutative two tori. So as such, the K0 group has two generators, the identity and E1, 2, the ripple projection, and we know what is the value of the trace. On the trace is normalized, so trace on the unit gives me 1, trace on 1, 2, it's theta. That comes straight from this statement. So, if you take any H, any Hamiltonian, for any gap projection that you see, the trace of this gap projection must take this quantized value. So it's always n plus n theta. and these are the labels, the CJ, the gap labels. And we can probe this by just computing the integrated density of states. So you take a finite volume approximation representation of this Hamiltonian, you count how many eigenvalues are there below some energy divided by the volume, and if you take this volume to infinity, this quantity is the same as this quantity. So here is the prediction. So I just took a few values of n and m, and I draw this quantity as function of theta, and I should see only straight lines with slopes which are integer. Here is the Hamiltonian, the generic Hamiltonian, and here is the integrated density of states calculated from this spectrum, and I should compare this picture with this picture, and it's 1-to-1. So that tells me that I indeed identified the algebra correctly. And moreover, whenever this index is non-zero, I will tell you in advance that there is topological edge spectrum. When I cut an edge, the gaps will be fully filled with spectrum. So let's see it again at work. So here is a pattern in 2 dimensions. The points are labeled by Z2, and now it turns out, so one should think of this as a perfect lattice perturbed by this term. The whole is the 2 torus. We have the dynamical action of Z2. In this case, it turns out that the algebra is the non-commutative 4 torus. So we are seeing the 4-dimensional integer quantum Hall effect in a 2-dimensional system. So here, the prediction is that the integrated density of states, or the trace of the projection, takes only these discrete values, and I took θ1 equal θ2, in which case you can see there should be line and parabolas, and this is a prediction. Here is how the spectrum of that Hamiltonian look like, and when I compute the integrated density, I get this image. I could identify every single patterns with a line from over here. So indeed, I identify correctly the algebra. And I can tell you that every time when one of these 3 labels are non-zero, there should be topological okay, so half an hour or something, maybe 20 minutes. I think I went a little bit fast. So, and this is actually quite a strategy. So now we are poking at interacting systems, and this is precisely what we do. We put spin chains on aperiodic systems, and we calculate the spectrum and the integrated density of states, and try to figure out how this pattern, how can we understand this pattern, and also we try to understand how to label this gap. So the framework goes both ways, from theory with prediction, but we can also start with numerical simulation and try to figure out the theory, that is the algebra. So how can I be so sure that okay, when these labels are non-zero, then I see topological edge spectrum? And first I want to tell you more what is in this picture. So in this picture I fixed θ1 and θ2. This is the bulk spectrum, and here is the integrated density of states. It is constant inside the gap, and inside the gap, each gap can be labeled by these K-Theoretic labels. Over here, I put a boundary, and when I put a boundary, I get something like this. But now I can sample the whole. So I generate the pattern again, but I'm starting from a different point from the whole, and here is if I sample the whole 100 points, and here is if I sample it 1000 points. The thing is, if I sample it 1000 points, all bull gaps actually fill up with edge spectrum. I can render this spectrum as a function of the whole parameters, and what I will find is that there is a whale. In fact, if I plot this spectrum as a function of the parameters available, it's a whale singularity. This, the whole can be also associated with the phasor. So the people here who work with the quasi-crystal, they know this notion about the phasor. What is the phasor? The phasor is just a point of the whole. And what I was telling here is that what is the space on which this phasor lives. So now, the core of the talk, the bull boundary correspondence. So, in my previous talk, I went a little bit convoluted with a representation, show you that the Hamiltonian have certain spectrum, and I ended up with an algebra. Here, I'm starting with an abstract algebra, which I will just describe it for you. So it's the algebra defined by D generators plus the functions, continuous functions over the whole. We have the same relations as before, but this guy is no longer a unitary operator, but is a partial isometry. So it gives me the unit in this when I put u star u, but it gives me unit minus the projection. And this, everything here is defined quite abstract. We don't know what this projection is. But the generic element from here is of this form. So it's u1 to the power n, u1 star to the power m coefficients, and these coefficients are taken from the algebra which is generated by these guys. So we leave u1 out. So this is what is theta. And then there is a canonical representation, and the canonical representation says that functions from here are represented as diagonal operators, very much like before, and these u's become the shift operator, but now projected on the half space. The shift operators which go parallel to the boundary remains unitary, but the one which goes against the boundary then gets this one. And E, when we represent E by this one, E becomes just a projection on the very last layer of the... So this is a half-space algebra, and through this canonical representation, I can generate any half-space Hamiltonian, which is a bulk Hamiltonian chopped off in all the bonds are chopped off along the plane. In addition, a boundary condition is put, so the sectioning is not ideal. The boundary algebra. So inside this half algebra, there is an ideal. So it's just all elements which have this projection in between. So it can be an element from this ideal is of the form A times E, A hat, E hat, A prime hat. And that's an ideal, and immediately, if you have an ideal, then you have a exact sequence of sister algebras. So this ideal embeds, belongs to the half-space algebra, and there is an evaluation map. The evaluation map is simply losing these hats on the U's, and this evaluation map takes me into the bulk algebra. So this exact sequence comes automatically. And now the exact sequence is split, so any element from over here can be written as one piece which comes from this side, so a bulk element move back, and one piece which comes from here. If I look at the representation of this piece, it comes to be the half-space bulk Hamiltonian, but now with Dirichlet boundary conditions. And this piece over here is just a boundary condition, is a Hamiltonian or a piece of the Hamiltonian which lives only close to the boundary. The key is here that this A hat is not just clean Dirichlet boundary condition, in fact it's a realistic boundary condition. So why did I tell you this? Is because if you have an exact sequence of algebras, automatically induces a K-theoretic six-term exact sequence of K groups. And this is the engine of the bulk boundary correspondence, and this is what Hermann Schulz-Waldes and Johannes Kellendorf found. Here is where our bulk algebra sits, and here is where we have projection, and here is the boundary algebra. So we have a map, which is standard map, which takes us the projection, the class of the projection, into a unitary from the boundary algebra. So we have a connection between bulk and boundary, which is made over here. If we have chiral symmetry, then one will use this corner. So in chiral symmetric systems, the topology is encoded in a unitary operator. So the topology sits here in the bulk, and it's taken in at the boundary into a projection. But now we will be just talking about this corner. So to establish the bulk boundary correspondence, one needs to calculate the algebra, then immediately knows what the boundary algebra is. Calculate the K0 group, calculate the K1 group, which is the same thing as the K0, but with projection replaced by unitaries, and in the same time understand what the exponential map does on the generators. If you have that knowledge, then you can tell very precisely when you have non-trivial bulk boundary correspondence. So in the case when this one is just a non-commutative torus, I recall that the elements of the K0 group, they have the generators. The generators are labeled by sets of indices. Same over here. Finite number of generators. The generators are unitary, labeled by subsets of indices. And we know very well how the generators are mapped by these boundary maps. As a result, I can make this statement. So, if I have a gap projection and I am able to calculate its decomposition in the generators, then if any of these, say, CJs, which contains the index number 1, are non-zero, then the spectral gap is fully contained in the spectrum of the half-space Hamiltonian. So in other words, the spectrum of this one covers entirely the bulk gap. So that's the spectral statement, and it is entirely made with the use of K-theory. And how the proof goes, it turns out that if this is not like so, then this, if this one is not like so, then this element over here is just a unity, and the class of the unity is non-zero, but that cannot be precisely because of this condition. So it's a very precise statement. It's independent of the boundary condition, and it applies in the regime of, for aperiodic patterns, but it does require a spectral gap. So that was my last slide, and let's see, this is my very last slide, and see what happens to the quasi-crystals and why don't they have topological aspect. So here is a one-dimensional quasi-crystal is generated by this cut and project scheme. I can fold all these into a torus, and this line. So now I will tell you how the pattern is generated. So this is a torus. This side identified with this side identified with that side, and I take a rope, the red rope, and I start winding this rope on the torus. So as you can see, I'm going over here, I'm coming back here, I'm coming back here, coming back here, coming back here, and so on. Here I have these blue lines, which are called the transversal. Every time when the red line intersects the blue line, I put an ink dot. And then I unwind this rope, and I see a pattern of points, and that is my quasi-crystal, generated by cut and projection. As you can see, it's a very dynamical procedure. If I take the same Hamiltonian and I diagonalize, I get this spectrum, and here is the integrated density of states. You cannot see, but they are the same labels. It's the same labels as for the pattern generated with the circle, or the sign pattern. So the K-theory is the same, has two generators and the same labels. And here is what, I took a theta, and these are the gaps, these are the labels, and when I cut an edge, no matter how fine I sample the hole or the phase-on, the gaps remain clean. There is no spectrum over here. So what's going on? It turns out that the points of this, in the whole pattern, in fact, is one-to-one in equivalent with the points of this line. And this line, if there were no complications, this line closes here into here, it will be a circle. But since the line is discontinuous, I have to remove this point. Not only that point, but in fact I have to remove the entire orbit of those points. And when you do that, in fact, out of the circle you remove a dense countable set. You are left with a Cantor set. And it turns out that the boundary algebra for such a Cantor set is trivial. So then, when you look at this map, the K1 group is trivial. There is no way to get non-trivial full boundary correspondence. So, in other words, the phase-on for a quasi-crystal doesn't live on a circle as you will be inclined, but rather it lives on a Cantorized circle. And the Cantorized procedure was shown over here. And this is why quasi-crystals do not have topological S spectrum. If you go in 2 dimensions, if you put magnetic field, of course you will get non-trivial topological S spectrum, but without a magnetic field you will not. So then I will stop here, and I'll thank you for it.
Is it possible to obtain some kind of Hall conductivity from your gap labels in K-theory? Maybe you said that.
Yes. So I'm going back to this one. So this is just the trace of the projection. So that the 0th Chern number. The first Chern number will be the derivative of this one with respect to theta ij. That will give you the whole conductance with respect to coordinates ij. The second Chern number will be the second derivative, and so on. There is a hierarchy, and it's all obtained from this one.
These are all electric Hall conductivities.
So these are, so the first one will be the first derivative will be the Hall conductance, and the other one are nonlinear Hall conductivity. So it will be the derivative of the Hall conductivity with respect to the magnetic field, second, and so on.
So always integers.
So it turns out the values of those are non-integers. So when you put magnetic field, they are not integers. And if you want to see what is the range of those invariants, they are all listed in our book. And it is only the top invariant which takes the integer values. And it is only the top invariant for which one can establish an index theorem, and as such one can go into the regime of strong disorder.
Thanks.
Yeah, you define some quasi-periodic structure in 1 dimension, 2 dimension. And later you say this, they are not quasi-crystal. So what's the difference between this quasi-crystal and the quasi-periodic bound lattice you define?
Yes, so in a going all the way back to
Maybe in 1
my
dimension,
head.
yeah.
So a quasi-crystal has finite complexities. The values of these E's are always a finite number of values. So this one takes value in a finite set.
I see.
So,
that's like
so in other words, this is the alphabet of the quasi-crystal. The alphabet is always finite. For
the
a quasi,
value of alphabet is fine. Okay.
yeah, the alphabet. For a quasi-periodic one, this alphabet, it's a continuous. This D stays in a continuous.
I see.
And it's a big difference, and there were many mistakes made in the literature and the community who study quasi-crystal, which is quite large and vibrant. They cringe when they see that people don't see the distinction between quasi-periodic and quasi-crystalline. So the quasi-crystalline, these D's are always take a finite number. The alphabet is finite.
But whether quasi-crystal is a special case of quasi-periodic, which this decomposition of who all can be formulated.
So I'm going over here. So this line over here ends over here and it continues. For sure, this line I could in principle approximate it with a smoothed version. So you will say that this guy, it's an approximation of a quasi-periodic, but the limit is truly singular. So as you take the limit, you will see that the spectrum, which for quasi-periodic we have seen is topological, it gets thinner and thinner, and at the limit you get gaps.
But for quasi-crystal, you still can have this decomposition, study algebra on this, so who to study
the whole,
quasi-crystal.
it just
That one still works.
it just turns out that the whole, instead of being a smooth manifold, is just a
You can find a site. Okay.
Now let's see if anybody noticed something special over here. You see, as I'm walking from gap to gap in this spectrum, I'm not crossing any spectrum. So if this is how the spectrum will look for the Hofstadter Hamiltonian, there will be no plateau transition in integer quantum Hall effect. So if I'm showing you this other spectrum, like here, every time when we jump from one gap to another, I'm crossing the spectrum. So it's a big difference. In this case, I can define a Chern number via differential formula. It cannot be defined for the quasi-crystal. So the only variant we can define is really the K-Theoretic ones, and it really shows that. Okay, again the difference between the two.
So the system, like the matrix of the Hamiltonian you have, is assumed to be Hermitian.
Yes.
Can you also apply the non-Hermitian matrix, non-Hermitian system?
Yes, it is. So at this level, yes, because the K group are in fact defined not for just projection but for idempotence. So you lose P star equal P condition, so that will cover also the non-Hermitian. So if you plot the spectrum of this non-Hermitian, you identify an island of it. This island might be on the real axis, might be somewhere in the complex plane. There is a Riesz projection you can define over it, and that Riesz projection will give you a K-theoretic class. So as long as one talks about spectrum which is isolated from the rest, that means spectral gaps, things will go through, but it will not go through in the regime of strong disorder. So in the regime of strong disorder, this Hermitian condition is, if it's violated, then the index theorem cannot be formulated, and the top topological invariant is not stable in the regime of strong disorder.
Any other questions? No, let's thank the speaker.